Hi everybody, welcome to CS Breakdown, and today for the second video in our approximation algorithm series, we're going to be talking about the maximum float problem. So the maximum float is actually something that would only be considered back when checks were a really common method of payment. You can consider some corporation or perhaps a bank or even an individual, and they have a certain fixed amount of money. Let's say they want to transfer that money to another bank, corporation, or individual. In doing that, they could write them a check, and that check would actually take a certain amount of time to be cleared. And in that amount of time, the money is sort of floating in the air, hence the term float. And it's going to be in their bank accounts, but it's going to be owed and technically already paid to the opposing corporation. So they've already paid somebody, but they still have the money. Now, the point of the float then is that they want to maximize the amount of time they can sort of float this money in the air so that they can actually accumulate interest off of that time. So while it's still sitting in their own bank accounts and the check hasn't cleared with another bank, then they're able to accumulate interest on that money despite the fact that they technically don't have that money anymore. So the problem then for the maximum float approximation is to find a way to optimize the float for a given, let's say we're a corporation. So we're trying to open K bank accounts to maximize our float. And we're going to be using sets B and P to represent all of the banks that we could possibly open an account with, and P represents all of our regular payees. So we can also define V of I and J, which is always going to be greater than 0, as the value of the float generated by paying person J, who's an element of P, and from bank I, which is an element of B. So what we're saying is you can create some value function, and in this case we're just going to call it V of I of J, but this will actually take into account the time it takes for a check to clear, the interest given at bank I, and a few other factors. So there's other things we would be considering in a real application of this, but for the approximation algorithm side of things, we're going to not really actually calculate, say, the interest at a bank and see what kind of values we'd get. We're just going to talk about this sort of more theoretically. So given this setup then, the goal is to find a set of banks such that the cardinality of that set is going to be less than K. So your goal number of banks is K, and you're trying to optimize the sum of the payments to person J from bank I. So this kind of looks like a confusing statement, but really all it's saying is for every person you're paying, so this is your summation portion of the formula, for every person you're paying, you want to maximize the float that you get by paying them using bank I. So you can try paying them from any bank, and whatever one will provide you with the highest float, let's say it's the one with the highest interest rate and the longest time it takes to clear a check, that's the one you're going to want to pay person J with. So you're trying to maximize this. So we can represent this using V of S as an objective function for the set S. Now, the approximation algorithm we're going to use to try to solve this problem is going to be greedy. Keep in mind that the purpose of approximation algorithms is to not have to do the heavy computation it takes to find a purely optimal solution. So we're going to be finding just a good enough solution that we're satisfied. And really, the solution is actually quite simple. All you need to do is take the next bank that increases the objective function most. So that V of S that we previously defined will be based off of certain factors. It's going to take into consideration the time it takes to clear a check, the interest rate at a given bank, etc. And whatever bank payment maximizes this objective function is going to be the bank we're going to choose to pay person J. So if we were to write this out, it would actually look like this. So whatever bank maximizes the function V of S union I, so given bank I minus V of S. So what this is really saying is just the set including bank I or the set not including bank I, and we're maximizing the difference between them. So the set not including bank I would be the set at the previous iteration in the algorithm, and the set including bank I is the current iteration in the algorithm. So the difference between including bank I and not including bank I needs to be as large as possible, which is really just a fancy way of saying we're taking the one that gives us the largest value. This is just how you would write it out given the notation that we've already defined. So this process is what we would do until the cardinality of S, or pardon me, it would be while the cardinality of S is less than or equal to K. Now, this isn't going to be optimal all the time, but it does provide a maximum performance of 1 minus 1 over the exponent. So there's kind of a fancy way we get this ratio, and it's going to be a little complex, but hopefully you can follow along with some of the math that we're going to go through. The first thing we need to do is set up a few preliminary things. We can say S of t is the greedy solution after t iterations. So S is the set of banks we're trying to find. Well, S is less than K, because we're going to pick K banks, or at most K banks. Now, given this notation, we can say that S of 0 is the empty set, and S of K is, of course, S, our final solution. Consider the objective function we previously defined, and we're going to set this to be our base case, saying that the value here, the value of an empty set, is going to be 0, because this was the minimum we said we would deal with earlier. Now, lastly, we're just going to say that A is representative of an optimal solution in this problem. So, given this notation, we can say that the value of S after t iterations is equal to this formula I've presented on screen. And it looks a little hairy, but I'm going to break it down and we're going to explain exactly what each portion means. So the left half of the plus sign says 1 over k and VA. And let's just consider what V of A is first. So V of A, we defined A is the optimal solution, and V is our objective function. So our objective function for the optimal solution is going to give us the highest possible value. Now, V of S of t is of course going to be greater than 1 over k times this amount, because we can allocate shares of the value to every bank. So let's say we have 8 banks and k is equal to 8, then 1/8 of our final value is going to be associated with each bank, approximately. Now, after t iterations, our formula is going to be greater than the 1/8, so one specific share of the optimal solution, plus 1 minus the remaining share from the previous iteration. So that's where V of S to the power of t minus 1 comes in. So to use this in our gathering of that previous thing I said before, the 1 minus 1 over the exponent is going to give us some interesting properties. So we can start here and say that V of S is equal to V of S to the power of k. This is a trivial definition based off of what we mentioned prior. Now we can apply the inequality we just defined, and we'll say that V of S of k is greater than or equal to 1 over k V of A plus 1 minus 1 over k V of S at k minus 1. So remember what this means is 1/8 of the value of an optimal solution plus 1 minus that portion of the solution prior, so the solution in the previous iteration, that's going to be less than the current iteration's solution. Now what we can do next is actually reapply the inequality, and this is what's been highlighted in red. So everything on the left half of the red brackets is the original from the previous level in the equation, and now we've just reapplied it to V of S at k minus 1, and now you'll see we have V at S at k minus 2. And you can see that this is kind of going to continue until we get all the way down to the base case. So eventually what's going to happen is you're going to get a lengthy series of this summation, and you're going to be able to simplify that to this. So 1 over k times V of A is of course just the same as V of A over k, and this is then going to be multiplied by what would be our large summation, but it's now simplified into this fraction. So it's 1 minus 1 minus 1 over k to the power of k. And that's because we performed k iterations to find k banks. So this fraction here is sort of representative of the number of iterations it took given the amount of value we'd be able to take at every iteration in respects to the value of an optimal solution. So now we can say that this is a 1 minus 1 over exponent approximation algorithm because this actually acts as an upper bound. So 1 minus 1 over the exponent is actually slightly larger than this function here. So v of a 1 minus 1 minus 1 over k. So if we were to consider k, of course, to be x, we can actually take a look at this output, which I've gathered from Wolfram Alpha. And you'll see that 1 minus 1 over x compared to e to the power of negative 1 over x, which is, of course, just the fraction I had to flip, it's going to act as an upper bound. So you'll see that it's asymptotic to the exponent function. And that's why we're able to say that this is a 1 minus 1 over e approximation algorithm, because its upper bound is always going to be this limit. So this is the absolute maximum performance we can say that we expect out of this approximation algorithm. So the greedy algorithm in and of itself is actually quite simple, and I didn't even really highlight it because all you need to do is take the next best bank based off of your objective function that you have to define. And of course there's different ways to define it, but really this is the proof of why this actually works. And now we've been able to formally find an approximation algorithm that runs in a very good time. So it gives us excellent output, and as a performance measure, this 1 minus 1 over epsilon is going to be fairly good because we usually consider certain approximation algorithms as 2 approximation algorithms or 5 approximation algorithms. But in this case, we were able to find a simple greedy algorithm with a tight performance bound that we've shown mathematically. So this concludes the video for the approximation algorithm on the maximum float problem. Thank you for watching. I hope you enjoyed. Please be sure to like and favorite and check out our other videos on CS Breakdown.